going to solve today's Geeks for Geeks problem of the day. Given a positive integer n, you need to count the numbers less than or equal to n having exactly 9 divisors. So in the test cases, we have given a number n equals to 100 and its output is 2. As there are two numbers 36 and 100 which have exactly 9 divisors and also less than equals to 100. For second test case, n equals to 200 and this time output is 3 as 196 is also a number which is less than equals to 200 and exactly have 9 divisors. Okay, so it's quite simple if we think with brute force solution. What I can do, I can iterate from 1 to n, and for each number, let's say m equals to 1 to n, and for each m, I will check that number if m is m have exactly 9 divisors or not. And how I can implement this function? Simple, just run a loop from 1 to m and keep checking that the number m modulo I is equals to 0, then increase the counter. Means you get a factor. Okay, factor or divisor, both are same thing. Okay, so in this way, you can count all those numbers from 1 to n which have exactly 9 divisors. So what would be the time complexity? It would be nothing but n square in the worst case, right? But as n is less than equals to 10 to the power 9, then it would not be accepted. So I should have a better solution. Okay, if you know an algorithm, square root algorithm, what it does, it returns all the divisors of a number in square root time complexity, right? In square root of n, it can give all the divisors. So now I can implement function with square root algorithm, right? And now it will take, so the outer loop will be again from 1 to n, so it would be n into square root of n, right? Yeah. So if we check number of iterations, then it would be 10 to the power 9 and multiplication with 10 to the power 5, and it would be 10 to the power 14, which again not going to submit it. Okay, so we require a better solution than this. So now I can optimize, since I can find all the divisors in root n, that is the base complexity can is possible. So I must, I should reduce the iteration count for the outer loop. So how I can reduce the number of iterations for the outer loop? From the observation. What observation? Like if you see 36, this is just a hit and trial method, and the 3600 and 196, right? Three numbers in the test cases are pointed as the valid numbers, right? And if you see these numbers, these all are perfect squares, and it is proved that all those numbers which are going to included in the answer will be the perfect squares only. So what I can do, I can find all the I can find all the square roots of the which are less than equals to 100, right? So not square root but the perfect squares. So I will store the perfect squares, right, which are less than equals to n. So it would be of maximum square root of n. Okay, and I will iterate over only these perfect squares. So now the problem has reduced to, it will be again be implemented using the square root algorithm. So yeah, so now this approach will be solving the problem in. So now this time I'm not iterating over all n's but only the perfect squares, which at max will be square root of n. So square root of n. Now if I count the number of iterations, so it would be 10 to the power 5, multiplication would be with 10 to the power 5 over square root, and then it would be 10 to the power 3 or 2 somewhere. So at max it can be, it would be 10 to the power 8, right? Okay, so it it can be submitted into the into any of the coding platform. Like I'm at GFG, so it can also be accepted over here. And if I write the algorithm, so it is the complete algorithm for, yeah, for this approach. So it is taking just the square root of n into square root of square root of n, and I'm just traversing over all the primes, all the perfect squares, sorry, perfect squares, and I will check with square root algorithm that I will iterate only for the square root of the square root of that number, right? So okay, and I will keep checking and increasing the counters, and at the end I will count that okay, I have this much number of divisors for that numbers. So I will check if it is equals to 9, then I would increment the answer. So this approach can solve the problem and also reward you the 4 points of for this number, right? But if you analyze the time complexity, it is saying that the base time complexity is square root of n into log of square root of n. So how I can solve this problem with this much time complexity? So for that, I need to analyze some deep mathematical concepts, like any natural number can be represented into product of primes, right? You know, p1 over a1 into p2 over a2, and like that, right? And also, if you find number of divisors, then how you can find number of divisors? Then I would take all the combinations of the powers of these numbers, these primes, sorry, these primes. So if a number like 44 can be represented in form of 2 to the power 2 multiplication with 11 to the power 1, and it is having exactly 6 factors or divisors. How I can find this? If you see 2 has the power 2, it means I have three combinations. I can have three possibilities for the power of 2, that is to the power 0 or to the power 1 or 2 to the power 2. So I have three possibilities for the 2, and similarly I have two possibilities for the 11, that is 11 to the power 0 or 11 to the power 1. So in this way it would create total 3 into 2 equals to 6 combinations, and all those combination creates a factor. So it creates a important formula that number of divisors is nothing but equals to uh, powers addition 1 product addition product a2 plus 2, sorry, plus 1, and likewise. So okay, so this is a important result we can use here. We have exactly 9 divisors. It means 9 equals to a1 plus 1 into a2 plus 1, or some likewise. Okay, so if 9 has k prime factors, then I can write the number of divisors as this, right? So ak plus 1. Okay, so okay, now I can take the combinations for the 9. So I can represent 3 into 3, or 9 into, sorry, 9 into 1, right? Only two possibilities to reduce the 9, right? And if you observe that 3 into 3 will leads to the power as p1 to the power 2 multiplication with p2 power 2. Yeah, so there should be two prime numbers whose square multiplication would lead to create that number. Okay, and for 9 it would be like, if we have p1 over 8, right? 8 plus 1 will lead to 9. Okay, and no possibility for the 1, so I will ignore that. So now I have one more conclusion, that the number which satisfies this condition, that it has exactly 9 divisors, then it must be of the form of like then they must be of the form of these two possibilities will be there, that that the number can be represented in the squares of the two primes or eighth power of a prime, right? Okay, so this is a very important conclusion we get. Now I can use this. So let's back to the solution. So okay, so what I will be taking, that I will first find all the primes, because now since we are going to deal with all the prime numbers, so I should have the list of the prime numbers which are uh, less than equals to the square root of the square root. Why I'm saying square root of the square root? See, since we are going to only check for the square root number of times, as I had discussed in the previous approach, that I just need to iterate over the uh, iterate over the square root times only. And now the square root of the number, because I just need to check for the square root of the numbers times only. I had discussed earlier it also. Now I made a array is prime, which will store that if a number is a prime or not, right? And I will run a sieve of Eratosthenes algorithm here, that I will uh, after the algorithm I would have all those numbers which are prime or not prime, right? You can if you don't know about this algorithm, you can go any YouTube random video and just check that and come again back to this solution. So okay, so I'm assuming you are okay with up to this mark. No, only the prime numbers. Okay. So as we discussed earlier here, that we will try all the possible pairs of the primes which are less than equals to square root of the number, right? So okay, so we just uh, check for all the pairs of the primes. So okay, I will run nested loops. First, I'm checking for the power of it. That if a power of it is also less than equals to n, then I will add into the answer that number also, and i- and then I will be checking for the um, pairs of the two primes, right? I will run two nested loops and make all the possible pairs of the primes and taking the product according to the p1 square into p2 square. And if the number is less than equals to n, then it means that number is also a valid answer. So yeah, just a simple implementation of the algorithm is not that much complex or tough to understand, but the intuition behind this algorithm is most important part of this of making this video. So hope this clears to you. Okay, so thank you.